So this will be my setup. In general, I recommend something similar if possible. Let me just... Okay. So I have the terminal on my left side where I will get on the cluster and do all the work, as well as the tutorial open. In principle, you can also have some other tabs open, which I will show you in a second. But first, please open the tutorial, because we will copy and paste some stuff over to the cluster. And here I will log onto the cluster. So I will SSH with my username and the IP. So this is the IP of today's cluster. This will prompt you for a password. This I saved on a separate window. You enter the password. So if it's your first time logging onto the cluster, you will also be prompted to trust the cluster. You can simply say yes, and then you will get on this cluster. And you see already on logging in, some things are already loaded for you. So we already loaded the newest release of FHR-AIMS, as well as some tools that we will use. So this is mostly a Python environment with the packages that we need to do the post-processing. So we'll wait just a few, maybe half a minute or a minute for all of you to get on the cluster. In case there's an issue or problem for you and it does not work, please let us know. And then we can still help out. In the meantime, I can just open the current window just so you see what is on the cluster here. Again, feel free to use the Q&A or chat box, or even just raise your hand. We are also able to simply allow you to speak in case that's something you prefer. Okay. Then, unless we get any complaints that it does not work, I will start with the tutorial now. So this should be your home directory. It should look very similar to what I have here. So we have a README. We have two different scripts. So the FHR-AIMS job is this submission script we will use for all the calculations. And these should always then be copied into your local folder where your FHR-AIMS input files are. And then we have this AIMS plot compare script. So that's just a post-processing script, which we'll use later on to plot some band structures. And then we have a solutions folder, and this will be used for the parts of the tutorial that are a bit too expensive to run in just this 1 hour. So we prepared all this beforehand, and I will show you later on what we have to do with these solutions. So to start, you should now have also the web page open for the tutorial. There's some introductions here and so on, as well as the prerequisites. All this we don't need because, as I mentioned, all the FHR-AIMS binary, as well as all the Python environments and so on have been pre-installed for you, so you can skip right ahead. We have a lectures tab also, so those are some old lectures on both GW and RPA. And of course, we have now the webinar from yesterday, which you can watch as well to get an introduction into the material. I want to just have a brief excursus here on the basis sets. We will see this in action also in the tutorial coming up. But in general, it's important to know that for correlated methods, so that's GW, but also RPA, BSE, coupled cluster, and so on, the basis set convergence is much more difficult than standard DFT. So here's some background. We're not going through all the text now, but in case this is interesting to you, please have a look here as well. So we have, if you've seen the basics video, species default for ground state DFT that are well known. So for example, the light, intermediate, and tight tiers. And we have specific GW defaults for the solid GW parts. So that's intermediate underscore GW underscore GW for tight as well as really tight, which has some forks, basis functions that are put in on top of the normal DFT basis sets. And this is actually works quite well, as we see later on, for the convergence in periodic GW. For the molecular part, you can use, of course, also correlation consistent Gaussian type basis sets. So that's the Dunning based sets or others, which are explicitly which were explicitly made for these types of things in quantum chemistry, so especially for correlated methods. And this allows you to do some nice extrapolation, as we will see later on as well. So within FHR-Ames, you can also just use Gaussian-type basis sets. You don't have to use the numeric atom-centered orbitals, something you will see in a second as well. So feel free, we have some other valence correlation consistent basis sets here, as well as these tier 2 plus arc2 basis sets. So these are all specific basis sets we have developed for different parts, and which are all described in the different publications down here. So if you to have a look, we'll go through some of these during the tutorial. So what we'll start with is here part 1, GW and BSE for molecules, and just the first tab, which is the GW eigenvalues and photo emission. So that will also be the largest chunk of today's tutorial. And the idea and what we want to look at is the ethylene molecule. So that's C2H4 here. And this is the well-known photo emission spectrum from experiment. So we want to try and replicate some of the spectrum, so specifically the ionization potentials of the HOMO and HOMO -1 and -2 with different methods to see, what kind of results we can get compared to experiment. And to start, we don't go right away to the GW part. We'll start with simple DFT. This is the well-known ionization potential theorem, which probably all of you know. So the ionization potential of the HOMO can also be written as the negative value of the Kohn-Sham energy level of the HOMO, right? That's, of course, only exactly true if you have the exact exchange correlation functional within DFT, but we will see later on this was a quite good approximation even then. So to start, you have here the option to always copy the comments that are written here. We'll make a new working folder. So I will copy this, put it here on the cluster, and then you should have, or you should be then in this GW tutorial folder, and then here we'll calculate the PBE eigenvalues of this molecule. In FHR-Ames, the geometry.int file is responsible to have the, or contains the atomic coordinates of whatever material you're studying. So this is just the ethylene molecule. There's a question from Vlad. I will allow you to talk now. So you can unmute and then ask a question if you like. Hi.
Could you please put the page URL of which I cannot find it of tutorial?
Is this already the chat, James? I think so, right? So maybe can you open the webinar chat? There should be a chat box. Otherwise, we can also send it to you directly.
Oh, just can you put it again in the chat, maybe?
Yeah.
Yeah, I sent it to you again directly and to everyone as well. And then, yeah, it's part 1 of the tutorial.
Yes, I see it.
Okay, great.
Yeah.
Yeah, I hope that works for everyone. Thank you. So I will disable talking now, Vlad, but of course, feel free to raise your hand again if you want to ask another question. Okay, so this is the geometry file. So that's simple ethylene here. I'll hide my controls. Throughout here, I will use Vim as a text editor. Feel free, of course, to use whatever you prefer or you're used to. So we should then have, oops, here I, of course, misspelled the geometry file. So it's important that actually the geometry file has the correct name. So it has to be called geometry without any spelling mistakes, because the code needs to, or it's looking for this file explicitly. Then the control file, the control.int file controls the parameters that we use for the calculation, including the basis sets. So here we've already prepared this file. So in this case, it's simply we're doing a PBE DFT calculation. So that's spin unpolarized, simple DFT with our tight species defaults. So we will create a control.int file. Simply copy in what we have here. As mentioned, this is just a PBE functional with the tight species defaults. And this you should just copy in. And then here we have a brief box to again mention how you submit. So we have to copy the FHR-Ames job file that I already showed you in the beginning. to this local folder. So simply copy tilde the FHI Ames job and then submit. To submit, you have to just run sbatch and the FHI Ames job.sh file. This will submit the job. Then you can check the queue if you like. So user 3 is already running. Hello, user 3. And this is me. And we are running on the cluster already. This should be really quick. To check, you can simply open the ames.out file, scroll down to the bottom, and then if you see something like have a nice day, this confirms that the calculation is finished. So again, this is simple ethylene with a DFT calculation. This just runs in a second or so. Okay. Then the idea is we can, as seen from the theory above, we can compare the Kronstamm eigenvalues to the experimental ionization potentials of the HOMO, HOMO -1, and HOMO -2. So these are the experimental values, and we can find the same in our ames.out file. So you can simply search here for this part on the Kronstamm eigenvalues. This will be written in every single iteration of the SEF, right? So, but you can scroll down to the end, scroll up a bit, and then you should see here the Kronstamm eigenvalues. And these match, of course, also the results we have here on the right side. And you see here the HOMO level is this -6.73. Then you have HOMO -1, HOMO -2. And again, the negative value is comparable to the experimental values, as you can see here. The problem now is that just simple PBE is very inadequate to calculate these ionization potentials, as you can see. So the difference is around 4 eV, quite huge. You can, in principle, also do the same for different functional, for example, Hartree-Fock here. We will not do this here, but it's enough to simply replace the XC comment in the control.inward HF. So that's Hartree-Fock. What you will see then is an overestimation. So instead of having most of these levels then are slightly overestimated with the Hartree-Fock. Okay. Any questions to this very simple DFT part? Otherwise, I will move on to the next approach. Yep, there's a question. I will allow you to talk. Hi, Tata, I think is the name. Yes. Hi.
Yes, can you hear me, sir?
Yes, I hear you.
Yeah. Okay. So can you please repeat where we should like change for the functional, right?
Yes.
I couldn't follow that part.
Yes, of course. If you open the control.in file, which is in this folder, you see we have here the exchange correlation line. And if you want to do Hartree-Fock for this molecule, you simply replace the PBE with HF. And that's how you would do a Hartree-Fock calculation. So that's the only change you have to do.
So it is applicable for any other functional as well, like whatever we want.
Correct, as long as we have it in the code. So you have to check always the FHI Ames manual to be sure that the function is implemented and what the name is. So the name can, of course, differ. Within FHI Ames, you also have libxc integration. So if you want any functional from libxc, we can also input this here. It requires some more, slightly different structure for the exchange correlation line, but all this is described in the manual from FHI Ames, which is also available on the webpage, by the way.
Okay, thank you, sir.
Yeah, no problem. I will disable for you. Okay. Yeah. Then, if I don't see any other questions, I will go ahead. So the next part, something which was also mentioned briefly yesterday, specifically by James in this talk, there's also the Delta SEF approach. And we actually have a separate, more detailed tutorial on Delta SEF, specifically where you can constrain the basis functions or the different energy levels if you want to calculate anything more complicated. For ethylene, it's quite simple what you have to do. We don't actually have to have these constraints because the material is quite simple to describe. Feel free to just copy this comment here to create a new folder for this section, which is just called 2 - PBE Delta SEF. Then what we have to do is do exactly this comment. This copies for the charge +1 system, the control.int files from the previous calculation, which we stored here in the charge 0. So that's the neutral calculation. And then we have a system with a +1 charge. Why? Well, because here we can directly relate the energies of the neutral system as well as the positively charged one to get the ionization potential. So let's just run this comment here. Then we have to slightly modify the control.int file. Why? Because, well, now we have charge. Once you have charge, you have to account for the spin initialization, right? So the spin treatment we will use within FHR AIMS is the collinear spin treatment. So what you can do is you can just copy these two lines and add them underneath the exchange correlation line. So now we specify spin collinear as well as charge +1. Then what we also do, and this is something we do specific in FHR AIMS to avoid wrong initialization by the user either by choice or just by mistake, you are required to, to input also the initial moments as well as charges to the atoms you want to put them on. So in this case, both of the carbon atoms here will get the initial moment of 0.5 and the charge of 0.5. So you know where this extra charge sits on. So simply copy this line. The lines here always act on the atom before it. So these both initial moment, initial charge go on the first carbon, and then the other one go on the second carbon. Again, we have more sophisticated data SDF approaches where you can actually constrain the different orbitals in case it's necessary for your system. This is, of course, not always applicable to all materials in the simple way, but we are just mentioning it here for the ethylene. So what we then have to do, you added the initial moment, initial charge. You copy again the job submission here. So FHR AIMS.job in the current folder and submit. Again, this will run a calculation. Similar as before, this should be quite quick. So I can already open the output file, which is always aims.out in this case. Scroll down, and this confirms that the calculation is finished. So what we have now is the charge +1 calculation and the charge neutral one. You can run this comment here, which goes a folder structure back, and then outputs this line from the aims.out files of both folders. So that's the total energy of the calculation once it's converged. And if you run the comment, you will see you have a charge neutral energy of here minus 2137.7 EV around and minus 2127.1 EV. And the difference here is actually quite similar to experiments. So we have a value of around 10.62 electron volts for the ionization potential, which is for the HOMO, which is already very close to the experimental equivalent. Okay. So that's the, let's say, most simplest data SDF approach here, which is already much better than the typical simple DFT approximation. But usually you have to go beyond, specifically for more complicated materials. So whenever you have these kinds of charge electronic excitations, you really have to go to many body effects. And in this case, we will introduce the GW approach. Okay. Any questions to this part before I go to the next part on GW? Otherwise, I will wait a few seconds in case some people of you are still creating those files or just checking the outputs. See. Of course, if there's a question or something is not clear, please let us know. So here, in case it's not clear, so I call this here always the tight species defaults line. This should not be in the control.in file itself. Right? So this should be or is replaced by the full basis set, which was the one here above. But I removed this here just for a shorter text description. So please keep in mind this should not be copied in the control.in file itself, but rather should be replaced by the full basis set, in case this was not clear. Again, if you have copied everything here, this the basis set is already in. So you should just do this. Okay. There's one thing I wanted to mention in case some of you are not familiar with these species files. So we have these species defaults already prepared, and they come shipped with the code. So if you have the FHR code, you will get this folder as well, which is a species default folder. And this has a lot of different species defaults. So for example, the tight species defaults are here in this defaults 2020. So if you go to, that's the current defaults we have for the DFT basis set. So you have here the light, intermediate, really tight, as well as tight. So for this part of the tutorial, we use these tight basis sets, and these are really given for all the different elements, as you can see here. That's 102 elements. Okay, that's just a quick excursus on the species defaults, and these can be found also on the cluster in the shared folder with FHR aims and the species defaults, in case this was not clear to everyone. Again, in this tutorial, we have it already prepared for you, just so you can copy and paste. Okay, then I think let's go to the next part, which is the actual GW calculation. So again, as I mentioned, we go to many body effects if you want to accurately treat these charged electronic excitations in all kinds of materials. And what we need to calculate, and this was illustrated yesterday in the talks, is the GW safe energy, right? So it's this frequency integral here over G times W. So the one particle Green's function, as well as here the screened Coulomb interaction. I recommend really here this review article that Dorothea also mentioned yesterday, which is quite nice to actually get an overview of how GW works, as well as all the different numerical intricacies and algorithms you need to use to actually solve the GW equations. Okay. So then what you calculate in the end is the quasi-particle energies here. And you have the quasi-particle equation, which is this one, which is essentially what we use in the code to calculate the energies. And again, you have the quasi-particle energies on the left and right side. So this needs to be solved iteratively. Okay. For the one-shot GW approach, you don't do a full self-consistency cycle of the Hiddens equations, but rather you do a one-shot. So that means you do one step of the cycle, which is why it's called G0 W0. This is much cheaper. And it's essentially the same as saying the quasi-particle energies that you calculate are evaluated perturbatively on top of just a normal single particle calculation. So that can just be DFT or Hartree-Fock. And this is also something you can see directly here. So you have here your Kohn-Sham exchange correlation potential, as well as then the parts here from the self energy. So this is really a perturbation on top of the Kohn-Sham eigenvalues from the preceding calculation. But that also means that the calculation for single shot GW is directly dependent on the starting point. So that's the starting point dependence. In the following, we will do GW, so G0 W0 calculations on top of PBE. And this is what you see here with the at PBE. So let's start. Again, copy, we'll do a new folder to do these calculations. So that's, we create a folder 3 G0 W0 at PBE, as well as the tight basis. We copy the input files we had before for the PBE eigenvalues, and then we simply change parts of the control file. This is just so it's easier for us. to handle. So simply copy this comment, run it, and then you should have this folder structure here. You can take a look. So we are now in the type basis folder here in 3g.w.pbe, and we have the control.in geometry.in files from before. We have to change the control.in file now. And what we have to add for this specific case are these two parts. So here I've highlighted the lines in blue. Only copy these two lines, not again the type species defaults down here, but only these two lines, and add them below the PBE exchange correlation function line we already have. So what does this mean? So you do still a normal DFT self-consistency cycle. Then you do a quasi-particle energy calculation. So that's what this abbreviation stands for, quasi-particle energy underscore calculation with GW. And then it's still important to specify how we want to do the frequency integration. So in this case, it's the analytical continuation, and the type we're using is 1. That's explained here a bit as well. So it can be 0 or 1. So 0 would be the two-pole fitting, and 1 is the Pardee approximation. In principle, as you also heard yesterday, the Pardee approximation is more accurate, but can sometimes be also unstable. So sometimes you have to maybe go back to the two-pole fitting. But in general, I think it's recommended to use the Pardee approximation. And again, why we're using here the analytical continuation? Well, this integral for the safe energy, as you can see here, is an integral over frequency. And the safe energy, or these terms here itself, have a lot of poles in the on the frequency grid. So what you typically do to avoid these instabilities is solve the problem on the imaginary frequency axis, and then you map the problem again to the real axis. And one of those options is the analytical continuation. The other, which we'll learn for the core levels, is the contour deformation. So that's something we will do later on. But for valence states, as we're doing now, it's not necessary to go to the contour deformation, which is also more expensive. Again, I will not go into details of the two methods. Please feel free to look at this review article, which explains this also in more detail. Okay, so you have the control.in file here. You simply save. You again copy the submission script and submit the submission script. So my job should run. And then you will see again, you wait a few seconds for the calculations to run. You open the aims.out file, scroll down, and then you see here, okay, this calculation finished successfully. Have a nice day. We can just briefly check the timing. So this calculation here took 6 seconds on this cluster. So that's the GW at PBE calculation with a tight basis set. Before I continue, I will wait just so everyone has this output file who's doing the calculations. If there's an issue, please let us know. Or if you need any help to set up this calculation here. Yeah. I don't see any hands or questions for now. So this is a picture so you understand the output. So if we open the, if we open the output file again, scroll down a bit, and then you scroll up until you see these quasi-particle energy values, right? So scroll up a bit, and then you can see, okay, these are the GW quasi-particle energy levels. As said, these are done after the full SCF. And this is really what you do for the quasi-particle energy calculation, which is the formula you saw already earlier in this tutorial. It just nicely illustrates what the different terms are. What you're typically interested in is only the last term, which here is the quasi-particle energy of the different states. So as you can see, you also have state 1. So these are also the core states in principle. So that's why you have these very low values here. And the output here is also pasted again here for you to compare in case you're interested and want to see. So what are we interested in? To have a look again at the HOMO level. So that's here state 8. That's the last one with full occupation, where we have a quasi-particle energy of minus 10.19. And that's already quite much more comparable to the experimental value compared to the PBE reference. And again, you can do the same here for the HOMO -1 as well as HOMO -2. And these already agree quite well with the experimental results compared to the PBE. Now, something you might have noticed, in case you're already familiar with GW, is I have not spoken too much here about the basis set. So we actually used the type basis set, which has been optimized for DFT total energies. And as you can imagine, for correlated methods, this basis set is actually not enough to get a converged results. And we'll show you this now. So we'll take a look here at the specific GW convergence with respect to our DFT basis sets. So copy this to create some new folders to do this extrapolation. So this should give you in this 3 minus GW PBE folder a basis set convergence folder where we have the different tiers. Before I explain you what the different tiers are, I will simply say you can copy in these files from the previous case. So that's that's simply copying the files from the GW calculation with the type basis into all of these folders. Okay, so oops, tree is not available here, but this should mean in principle in the tier 1, tier 2, and tier 3, you should then have the control.in and geometry.in files. Then when you also read publications with what is tier 1, what is tier 3, tier 2, and so on in FHI-AIMS, if you open the file again, so let's say here the tier 1 control.in file, and you look at the species default, so that's always starting here with this large part with the hashtags here. So that's the type defaults for the carbon. You scroll down a bit. Then you see here the basis functions. And these have already been grouped. So you can see these three basis functions make up the first tier. And these basis functions make up the second tier. And the same you will see for all the other elements. So when we say, let's try here a tier 1 basis set, what this means is everything else you will just comment out. So for carbon, we will simply just do the first tier, only these three basis functions. And then you try and check the same for the hydrogen. So do we have tier 2? Yes, we do. So this will also be uncommented. Okay. And in this way, you can do a tier 1 calculation. So that's the tight species defaults, but with tier 1. We can check the same for the tier 2, but the general tight defaults, I think, are already all tier 2 for these elements. So for carbon, as you can see, it's tier 2, as well as for the hydrogen, as you can see, it's tier 2. So this is all fine. And then for the tier 3 calculation, we have to go again and add some more basis functions. As you can see here in the DFT total energies for the free atoms, so here you are in the range of below a millieV. So just so you know, so tier 3 is already for DFT extremely converged, but we will see what happens for GW. So you should have for both tier 1, tier 2, and tier 3, all the basis sets now prepared. In case you're unsure, you can, of course, here just compare with our reference files, or you just simply copy them here into all of the 3 folders. So tier 1, this is the control file, that's the one for tier 2, and that's the one for tier 3. Now we do the submission. So let's go into tier 1, copy the FHI-AIMS script, submit. Do the same for tier 2. Copy in the submission script, submit. And then we do the same for tier 3. Oops, first copy in and then submit. These calculations are still very quick. If you are unsure whether the calculations are finished, you can either open all the aims.out files or you run something like this. So what I can do with tail is simply output the last 2 lines of a calculation. You see tier 1 is finished with have a nice day, tier 2 as well, and tier 3 is currently running. But again, this should not take too long. And now all of them are finished in my case. So I will wait a few seconds again for all of you to prepare the files and then run in. In case you're running into any issues, please let us know. And then afterwards, we'll continue with the post-processing of these results. Again, if there's, when we say tier 1 and tier 2, in case this was an issue for someone, here, when we say tier 1, you have to do it for all of the species files. So both the carbon and the hydrogen have to be tier 1. Okay, so always keep in mind both of the elements have to be at the same tier if that's what you want to do. So always comment out both of the all the different tiers for both of the elements in this case. Okay. Just so you know. And again, cross-check with the reference files just to be sure that everything worked correctly for you. And then we go here to the convergence part. Okay. So otherwise, I don't see any question. So what we'll do now is create a script, and I'll call the script the same as it's called here in the tutorial. So that's plotconvergence.py. I'll open that file and I'll simply copy paste what we already prepared for you. So the file itself is what it does. It takes these 3 tiers we created and just reads out these aims.out files and the energies. Okay. So simply save this file. Again, just copy paste. There's no need for you to change anything. And then in this folder, so please keep in mind you have to be in the basis set convergence folder and not in the different tiers. Simply run this command with Python. Again, on the cluster itself, Python is pre-installed for you. So it's enough to just run this Python command. After running, you should see a .png file. Now, on the cluster itself, you cannot open this file. So instead, what I'll show you now is we copy this to our local machine. So if I go here to my second tab in the terminal, you see this is just my local machine. I did not put anything here, but I will copy this file. And to do it, you do an rsync command, you do your username at the IP address, and then you do the folder. So in this case, basis set convergence is the folder I want to copy. Then you are prompted for your password. Copy, paste the password in. And you should see this folder here. And that's what we recommend. So in all cases, copy these files first if you want to open them. Okay. So the HOMO, this is the plot that you get. So you have the HOMO level with PBE as well as with GW at PBE, or G0W, not at PBE. And you can already nicely see. So one, the PBE is already extremely converged, even with tier 2. And you can see that GW does not converge as well. So going from tier 2 to tier 3, there's still a difference of more than, or like almost 100 millieV. So keep this in mind. These basis sets are not meant to be used for converged GW calculations. So that's really the takeaway here. Okay. I will go back to the cluster now. So are there any questions here for this part of the tutorial with the extrapolation here? Or not the extrapolation, the simple basis set convergence here. Okay. I don't see any for now. So I would continue with the infinite basis set extrapolation. So that's really now something specific for correlated methods for correlated methods in general. So what we see, it's much harder to converge these calculations with the basis sets. For the molecules, we can use, as an example, the Dunning basis sets. And these are also within the species defaults folder shipped with FHI aims. So you can simply use them directly. And they're stored, as you can see here, in the non-standard output. There is one Q&A from Hyungyong Kim. So in FHI aims, do we have basis sets for the following atoms: radium, palladium, and gold? I think so. but we can also have a look. So if we open the shared folder, and then I'm guessing, which one are you interested in? Probably the so it depends whether it's the underscore GW you're interested in or the Dunning basis sets and so on. So, but yeah, those should be available. But let's see, for example, here in the GW part for the tide. So that's the GW basis sets for periodic systems. You have here instead, you have here AU, you have platinum, and you have iridium. So the answer here is yes, and in the other case as well, because these are just the Dunning basis sets that you can use. So I hope that answers the question here. Okay. So then we do the infinite basis set extrapolation. And if you're familiar with quantum chemistry calculations, you have seen probably these ZZ minus PV and Z type basis sets. So that's the Dunning family with where you have double zeta, triple zeta, quadruple, and so on. We could do the same as before, but just to save some time, we have prepared this in the solutions folder. So that's something I mentioned in the beginning. If you want to copy this folder, you can simply do so by running this kind of command. So what we do is we go a folder structure back. Then we run the copy command. And then you should have an infinite basis set extrapolation folder, which you can go into. And here you can see we have all the different Dunning basis set calculations, and these are already finished. So we go from double zeta up to quintuple in this case. Okay, so feel free to skip this part of the setup, because again, all these calculations we have done, but you can see here, for example, these are indeed the CCPV, the Z basis set specifically for the FHI Ames code. But you can also use the basis set exchange in case you're more familiar with that to create these kinds of basis sets. And again, we have an extrapolate script that's the same here as the one already copied. So this script here is the same as we already have here. It again takes these different folders, reads out the energies here, and then it performs an extrapolation. To run, simply go down a bit and you see the comment. You only have to do Python and the extrapolate script. This gives you a .png file and gives you the end value. So indeed here we have something like minus 10.44 eV for the basis set, for the extrapolated value. So again, if you want to look at the actual image, I would encourage you to first copy these files. So rsync -r, add the IP, copy this folder into the local machine, again, copy the password, go into this folder and open the resulting PNG, in this case RBS, and you can see here, indeed this matches to what we have in the tutorial, what you get. So you have something like minus 10.44 eV for the HOMO level here. Okay, but you can already see, so that's here the quintuple zeta. So difference is still on the order of 100 millieV. So as you can see, it's quite hard to converge, even with very large basis sets, and that's why you have to do this kind of extrapolation to gain these values. Okay. Any questions on this part? Okay, I don't see any at the moment. There's a comment, I guess, from Kyung. The graph seems to have a quadratic term. You mean it's not a perfect line, you mean? Yeah, that's usually what happens. I mean, we do a linear extrapolation, but it's not always perfectly on this line. So yeah, that's just to really, I mean, but I think that's still common practice to do a linear extrapolation between the different tiers. And I mean, that's the reason the Stunning family has been created this way. So it's meant to be calculated in a hierarchic fashion. So if you go to two zeta, triple zeta, and so on, you should really be able to extrapolate this way. But yeah, it's not a perfect extrapolation, of course. Yeah, it's true. Okay. Any other comment or question here? I don't see any at the moment. I will wait a few seconds in case you're still running or copying files. Okay. Then we continue to the next part. And that's something we can also do. So you can, of course, also visualize the spectrum, right? So what we can do with the following script is just extract the quasi-particle energies, which we have, and then we broaden them into spectrum, right? Because why? Well, we wanted to compare our results with the photo emission spectrum from experiment. And you can, of course, just compare peak positions, but you can also try and create a spectrum to compare. And that's what we're doing here. So you can create this file, create spectrum inside this folder. Simply, again, copy and paste. And just as a general comment, you don't have to use these scripts in your own work. Feel free to write your own. We have just prepared these in advance, so it's easier to follow in the tutorial, and we don't have to mess around with too many things. So here I actually have to move the spectrum one folder structure back, as mentioned here, and then, oops, sorry. And then I can run this comment here, which creates the spectrum. So you do create spectrum, you specify the output folder. In our case, we want to do the most converged calculation. So that's here the quintuple zeta calculation we have, aims.out. And then we save this file into a spectrum -cc -pv5z.dat file. And that creates the spectrum file here, which you can use to visualize. Yeah, and in principle, we've also prepared this .dat file, which you can find also here in this GitLab tutorial. But in the end, what you see is something similar to this here. So if you visualize the spectrum, that's here the blue line in your local machine, you will see something like this compared to the experimental version, which is the orange line, which we have copied from the experimental reference. So that's, to recall, that's essentially exactly this spectrum here, just in the first few, in the energy range here. And to do this visualization, you can use whichever package you like or prefer. So you can use CLIMS, which is our command line interface with the XY plot infrastructure. And I can show you this in a second if you're interested. So if we copy this folder here to our local machine, then you should have now this 3 folder. And the spectrum file, what you can do is this CLIMS XY plot. Oops, here I did not activate CLIMS. 1 second. So you can do CLIMS XY plot and the spectrum file. And this will open here a Python interactive window. And then as an example, so here I'm something from -5 to 20. you can take a look, and the spectrum is indeed the same it is here. Again, the intensity is just different as I plotted here. But you can see this is indeed the same spectrum that you get, but feel free to use whatever software you like to use to plot these things. And again, this is CLIMS. It's also described again in the home section. So there's a section on where you can find these tools. So that's also a Python package. Yeah, and James is kind enough to install, given the pip comment if you want to install this on your local machine. Okay. Any questions here to this part? Because this also ends the section on the general GW intro for these molecules. Any question here? Okay, I don't see any. Okay. Any general questions to the GW parts in this section? So not maybe specific to the tutorial. Otherwise, I'll continue. So I can already tell you the next section will be on core levels. So what we've done here is mostly looked at the HOMO levels, so the valence states. But for the core levels, you have to be a bit more careful. So you cannot simply run the same GW calculations if you want to get accurate results for the core levels. So there are special considerations, which will be the next part of the tutorial. But yeah, I think for now, I don't see any questions here. Again, I recommend to copy all of these files to your local machine in case you want to do the post-processing. And again, the cluster will be closed at some point. So always remember to copy these files over. So then to go to the next section, what we do is we go here to part 1 and we go to the core level. So that will be the next section of the tutorial. So click here on core levels, and this points you to the next section. I already went one folder structure back on the cluster, so feel free to do the same. And then that's where we run these calculations. So what's the problem with core states? Well, if you want to do X-ray photo emission in experiments and you want to do the same with GW, you actually have to go to much more accurate integration techniques, as described here and also in this publication. And the approach of choice within FHR-Ames is the contour deformation, which is more expensive. So I think it scales n to the power 5 for core states, but it's much more accurate than the analytical continuation we already looked at in the first part. Another problem that can be quite severe is that the simple PBE starting point, so a GGA starting point as we had, can lead to multi-solution behavior. So that means you don't get an actual single solution for the problem. There are two ways to circumvent this. So one is you can use an you can use a hybrid functional instead of the GGA with a very large amount of exact exchange. So that can mean something like 40 up to 50% of exact exchange. Or you do partially self-consistent GW. So what you can do is eigenvalue self-consistent GW or GW not. So that means only the DFT eigenvalues in the Green's functions are replaced by the quasi-particle energies during the GW cycle. And this is here typically denoted as EV GW not. Or there is another option, which is more or less now, I think, the recommended option within FHR-Ames. You can use a level-specific Hedin shift approximation. And that's called here G underscore delta H W naught. And what this does, it applies a constant shift. So that's the shift here of the real part of the self-energy compared to the exchange correlation potential, which you can put in the quasi-particle equation. And this very nicely is very similar to the eigenvalue self-consistent GW naught, but it does not incur much additional cost. So you don't have to go through a full SCF cycle here. In this case, so it's quite similar in cost to the G naught W naught and gives much better results for the core levels. And that's the approach we'll briefly show here. Yeah, again, you have to do basis set extrapolation. So what we do here is a simple two-step or two-point extrapolation. So we use a triple zeta and quadruple zeta Dunning basis set to do this in this case. And as we'll see in a second, for core level states and GW, there's been some recent publication and work from Dorothea Scholz's group, who has shown that convergence can be accelerated quite drastically if you include SDOs. So that's like Slater type orbitals, which more nicely describe here the Cas condition at the nucleus. In another point, so you can already see it's quite complicated to get the core levels correct. The relativistic effects, of course, much more pronounced in the core region. So you have to go beyond. So what we use in FHA Ames by default is the scaled atomic Zorba approach. But what you can do in this core level GW, you can simply do an atomic correction, which is dependent on the atomic species. Again, something I will show you in a second. This is nicely summarized in this paper as well. So have a look at the references if you're interested in all these different parts of why these core levels are difficult to do. So what we'll do is this Hedian shift GW naught calculation. So copy here this comment to create new working folders. And this should give you these three folders here in this GW tutorial core levels. So we have a triple zeta, quadruple zeta, and this tier 2 plus SDO2. This we create in each folder. We can create a geometry.in file. Again, same molecule as before. We copy this file into the other folders because we're always looking at the same file. So I will briefly go over what the control file will look like in general for these core levels, and then we'll copy them in a second. So it's still a PBE DFT calculation beforehand. We then do a GW as normal, and this activates this Hedian shift G0W0 part. Again, this more or less approximates this eigenvalue self-consistency G part. And we do the analytical continuation as usual with the part approximation, here with 16 parameters, 200 frequency points. And then importantly, because we're looking at core levels for core level 1 and 2, we do the contour deformation. Okay. And then that just means we include all states in the eigenvalue calculation. And here, this is the relativistic correction. These values here come directly from the paper. So if you're unclear what shift to add for which species, so that's dependent on the species, have a look here in the paper 3, where exactly these values 0.3 something and 0.1 something are taken from. Okay. Now the number here, what is 1 and 2, is of course apparent if you do a DFT calculation beforehand, so you know, or you just know by chemical intuition which is the first core state and which is the second. Okay. Okay. Any question before I continue with the actual calculations on this part of the control file, or what we will do now for the core levels? Okay. At the moment, I don't see any. Again, I think most of these parts have been explained yesterday by Dorothea in detail. So feel free to also watch the live recording again in case you're interested, or read the papers. Okay, good. So what we then have to do, here's some more details on the SDOs, by the way, in case you're interested. I will not go here into detail of the exact basis sets that are used, but there's some more information here. So what we have to do is copy in all these different control files into the different folders. So let's do this here. For the triple zeta, I create a control file, I copy in, and I save. I do the same for the quadruple. Go to the next one, I copy in. And I do the same for the tier 2. Copy in and save. So now we have geometry.in and control.in for all 3 folders. Simply copy and paste. There's not much difference, or sometimes here it's just a shift of the lines, but the only thing that is really changing is the basis sets. Okay, so here we have tier 2 plus some Slater type orbitals. You can see them if you scroll down a bit. You can see them, for example, here. These are the Slater type orbitals that are added. Okay. And if this is done, you simply go into each of the folders to submit. So again, copy in the Aperture Ames job, submit. Do the same for the quadruple zeta. And do the same for the tier 2. We'll wait a bit. It's another user running. Should not take too long. Again, if you don't know how to check in case calculation is running, you can simply run this tail comment. You can see, for example, here, triple zeta and quadruple zeta is already finished. And we're still waiting on the Slater type orbital basis set to run. Did the quadruple zeta not run? Let me see. I think this finished, right? That's still running. Yes, that's why. So this runs, I think, for a minute or so. Here it's a bit more expensive because you have, for example, a contour deformation also for the core state. So keep this in mind. And of course, a larger basis set than you have with the typical NAOs. Let's check again here. So my last calculation is running in this example. Yeah, user 17 is still running stuff. Let me simply check again. So now you nicely see all 3 calculations are finished. And this is, for example, the output of the triple zeta basis set. So again, you can take a look at the quasi-particle energies, same output as in the first part of the tutorial. So you can take a look here. What you want are the 1s energies, right? So that's state 1 and 2. So we have something like minus 538 and minus 291. These are the 2 1s core states for the carbon and the hydrogen. And here we also will extract the total number of basis functions. So that's simply a line in the output, which you can search for. And again, we use this extrapolation, as we said here. It will look something like this. In a second, I'll show you how the extrapolation actually looks like. To do so, we use this script again. So run extrapolate.py, copy paste. If you are interested in the script itself, I mean, have a look at some point in more detail what we're reading out. But it's we're reading out the different folder, the output files, taking out the number of basis functions, and then also reading out the state 1 and 2 results. So that means for the 1s states here. Okay. And then, yeah, we do a simple extrapolation. Have a look at this script in more detail if you're interested. But what we do then is this just Python extrapolate.py in the GW tutorial core levels folder structure. And then you will see we're processing these 3 folders. Okay. It saves 2 extrapolations, one for state 1 and one for state 2 as expected. It will look something like this, and I will show you in a second. So state 1 here, you can see the script says something like minus 538.64 is the quasi-particle energy of this core state, which is indeed the same value here. Of course, note now this is a 2-point extrapolation. It will not be it will not be converged, of course, here. And but it's an approximation which is not too far away from the experimental value. So the experimental value here is the green dashed line. But you can see even the extrapolated value does not seem, is essentially as close here as the Slater type orbital basis set, which is much smaller, right? So the quadruple zeta is on the order of 0.3 to 0.4 eV, almost away from the experimental value, while here you have something like 0.2 as the difference for the tier 2 plus Slater type orbital basis set. And the same is true for the other part. So actually here you get a quite nice extrapolation to the exact value. But again, so here these are quite comparable for the 1s state for state 2 in the calculation. And again, what we used here, just so you know, is the Hayden shift G W naught approximation. So that's an approximation again to the eigenvalue self-consistent G part. So to verify that this is indeed what we get, I will copy over this file again to my local folder. So let's do so here. Then I get the GW tutorials folder and I get the 2 states. So let's open both. So this is state 1. It's the same plot as you expect here. And this is state 2. The same plot as you expect here. So indeed, this matches what we've seen. Okay. So there's another comment here. In principle, these correlation consistent Dunning basis sets in general have been optimized more for the valence states, but they're also core optimized ones. So these are these AUG minus correlation consistent ones. And the tier 2 SEO 2 basis set that we used here, so that's NAOs plus Slater type orbitals, is already quite close to these very large core optimized basis sets. Okay, so these are much larger than the actual NAO basis sets that we use, but the difference is essentially already very close. Is there any question here on this part? So that's for the core levels and what you have to be careful of. So at the moment, I don't see anything. There's an optional exercise here, which we'll skip, but you can also, of course, do the same with the eigenvalue consistent G, W naught approach. Again, as I mentioned, this Hayden shift approach is an approximation to this here. So you will see it's quite similar. But that's the part on the core levels. So for the core levels, you have to be a bit more careful if you want to get nice agreement with experiments and stable calculations. Okay. But then, because at the moment I don't see any calculations or questions, I would skip to the last part of the tutorial, which we'll go through a bit quicker because here we actually won't be able to run anything, and that's GW for the solids. So as mentioned, we can do both molecules and solids with GW, but the solids are much more expensive. So as an example here, so what we'll do in the tutorial is silicon, 2-atom unit cell with an 8x8x8 K grid and essentially and the intermediate GW species defaults. And this already takes around 4 hours on 288 cores. So that gives you an idea on how long these calculations are. So I would urge you here, please don't submit these because they will not be able to finish in time. Yes. Yeah, so this maybe I would hand over to Andre or James. So there's a question from Hungyom. Yes, you cannot copy to a local machine. Can you copy the I think that should be doable, right? We can make a backup of user 17 simply, and then you can go again in session 2 if you like. So that should be no problem. I think James or Andre will handle this in the background, so that should be no problem. Maybe they will just ping you again in case this is done, just so you know. Great. So here, as I mentioned now, we'll not do the calculations, but we'll look at the calculations in more detail. So what we do is here in the GW tutorial folder, we have the solutions already prepared, as I mentioned. So if you copy this folder here, you see several things for the GW for solids part. So all the geometry.in files will be the same. It's silicon. So that these are just the 3 lattice vectors as well as the 2 silicon atoms. This has already been optimized. So that was based here on HSE06 with intermediate species defaults. Something we have done in a previous tutorial of ours. Okay. Then in the GW calculation for the solid is slightly different. So if we take a look here at the first control.in file, which is this one here. Here it looks a bit worse because it's zoomed in, but you can also have a look here at the browser. So you still do a PBE on top as the initial calculation. You do here for the quasi particle, you have to put GW underscore EXPT. So that means it's more of an experimental implementation for the solids. And we do a 2-pole analytical continuation with 60 frequency points. It's an 8x8x8 K-grid, so that's already quite large to do with GW. And this is just here an optimizing flag. So that essentially speeds up the GW calculation. It's currently not a default, but it might be after some more testing. So this is currently being tested, but in general, this saves quite some time in the GW calculations. And what we are interested in the end is the band structure with GW. So you have this AIM-specific output infrastructure for the bands, which are all these lines. So for example, here we plotted the gamma to X band with 17 points. And then this is the structure. So you always have here the 3 coordinates for the first point, 3 for the second, as well as the K points in between. Okay, so just so you know more or less what the band structure looks like. This is explained in more detail in our basics tutorial. So you can also have a look here where we go through also the normal band structure with DFT for silicon. Again, feel free to have a look here in case you're interested into some of these keywords. Much more details are in the manual in case you're interested. Yes, here it's if you want the GW eigenvalues for the solids, you have to have the band output. So keep this in mind that this needs to be added. In this first calculation, we simply have the intermediate GW defaults. So that adds some additional functions to the intermediate species defaults for the DFT part, which are specific to these correlation methods, and in this case, GW. And if you take a look at this is what the folder looks like after running a calculation. So you have your different bands. So these are all the GW bands, as well as your AIMS output structure. So, and if you want, I will copy here the full folder to my local machine, just so you can see what happens. So if I copy the full folder here, and you can of course do the same. Then I go to GW for solids. In the first folder, I can run this CLIMS command, which I will just do here, to get the band structure. So CLIMS will read out in this folder the band structure and plot something like this. So again, this is interactive. So if you want, you can zoom in parts and so on. You can take a look, for example, if you're interested in gamma, you can take a look at gamma and so on. Okay. So that's simply here the GW band structure that we get. If you're interested in, I will go back here, in the band gap, you can take a look at the aims.out file directly, or you do it graphically, but in the aims.out, if you scroll down a bit, there is a point on the GW band gap, which is here, right? So that's, for example, here space direction 10, but in general, you look here for the total set of bands, so that over all of the GW bands, it looks at the smallest band gap. So in this case, we have something like 1.09 eV. It's the band gap. Yeah, and you can nicely see here it's not a direct band gap at gamma, so it's slightly offset for the LUMO. Yeah, so the numerically converted literature value is something like 1.12 for these GW values. So that's already, I think, very nice agreement, even with these intermediate GW basis sets. Then there are some additional things. In the interest of time, I will not go through all of them in detail, but we will explain all of the results so it's clear to you and what you have to think of. All of this you can also do on your local machine. So since you have all the results, you can simply do the post-processing as well. So one thing you can compare is how does G0 W0 with a PBE starting point is comparing to PBE or HSE06, so a hybrid functional. And for this, you can use this aimsplot compare script. So in case you forgot, this is given here in the local folder in your user folder on the cluster itself. In case you're interested, you can, of course, also download this directly to your local machine. So you can do this path and then simply copy the file to your local machine in case you want to do this after the fact. Again, this is just based on Python. So for example, if you have CLIMS, you can also directly use this aimsplot. Okay, and what we can do is we can run the script based on the different calculations. So for example, if you have a look here at this 2 comparison, you will see we have a GW calculation, an HSE, and a PBE, all with an 8 by 8 by 8 K-grid, and the same settings for the band structure. So to run, you can use this aimsplot comment. Oops. Yes, I have to do this. I have to use this script here, and this will save a file which is here. It looks something like this. I think here okay, this is not the correct offset. So you have to play a bit with the offset if you want to align the band structures here at the gamma point and the valence bands. But what it will look like in the end is something like this. So this is just the same band structure, just aligned at the valence band maximum. Unfortunately, this is something I think you have to do by hand, which we have in the solutions. So you can also take a look there in the GitLab. But yeah, what you get is something like this. So you see the band gap 1 compared to the PBE is, of course, opening up for both the hybrid and the GW. And there are still differences between HSE06 and GW. So in the valence region, it's quite good, as you can see here, even to like -10 eV. In the upper conduction states, you can already see quite a big difference, even between the hybrids and the GW. So that's just something to notice. In most cases, it's people say it's a constant shift. That's not necessarily the case. So you even have differences in some of the dispersion around. Yeah? But feel free to have a closer look at these kinds of results itself. Then, as done for the molecules, you can take a look at the convergence with the basis set. So in our case, we have the basis sets, these intermediate GW, tight GW, as well as really tight GW. And again, the difference is always these auxiliary basis functions that we add. So these have been tested and it's published, so you can take a look there as well in this reference 1, that you can use these underscore GW species defaults and FHR aims to get quite nicely converged results for periodic GW. Something we have here. So if you take a look at the folder 3 bases, you have these 3 folders. So you have an intermediate, that's intermediate basis set, intermediate underscore GW, really tight underscore GW, and tight underscore GW. And they build on top of each other, as you can imagine. And you get something like this. So you can use the script. I will skip this part here. Feel free to do it on your own in your local machine. But you will get a script which looks something like this. So if you go from intermediate to intermediate GW, the difference is very large. So just adding a few auxiliary basis functions adds like a difference here on the order of what 40 millieV. And the difference is much smaller if you go from tight to really tight. But here you are more or less converged in this region already on the order of a few millieV. What's important here is, of course, this is more expensive. So, for example, to go from intermediate to intermediate GW with the same settings, you are roughly going from 2.5 hours to around 4 on the same amount, of course. So just know it's more expensive, but the gain is, of course, the accuracy. So this is important. Another point is just the number of frequency points. So this is what we use for the frequency integration in the Ceph Energy. Again, if not familiar, take a look at Dorothea's talk yesterday or the literature. And you can plot exactly or directly this frequency dependence. This is just was the keyword inside the control.in file. Again, this has been prepared in the folder 4 minus frequency. So you have these 4 folders here. What you see with the same convergence script that you can get quite nice convergence around 80 to 100 frequency points. This is not necessarily the case. So as mentioned here, for silicon behaves nicely. But for some other cases, you might have to go to 200, on the order of 200 frequency points at times. So keep this in mind. But this is something you again have to check for your band gap. And the same here is just the number of K points. That's the last part. So if you go to your K grid, we simply change the K grid from a 4x4x4 to a 6x6x6 and 8x8x8. We are able to run the same convergence script again to get here the GW K grid convergence. And as you can see, there's quite a big difference already from 4x4x4 to 6x6x6. And the difference is here not too drastic, on the order of like 50 millieV or so for going from 6x6x6 to 8x8x8. But the scaling it's not very nice compared to the K points. So you have like here quadratic scaling with the number of K points. So keep this in mind. It depends on what kind of accuracy you need in your calculation in the end. Of course, if you really want highly converged calculations, you really have to go to larger K grids. But keep in mind that this is really extremely expensive in the GW part. And here, the same as I mentioned, silicon is quite nice, so it converges pretty quickly. And then here as a slight X course, as you saw, GW for solids is very expensive. But in general, we think it's better than the other approaches, for example, like hybrid density functionals, if you're really interested in very good band gaps and band structure, because it's less parameterized than, for example, HC06, where you have to optimize a parameter, which is often arbitrary, or a simple DFT, which of course is not good for the band structure in general and the band gap. But GW is really more expensive, but in the same vein, much more accurate and robust. So keep this in mind. Yeah, and with this, we're at the end of this tutorial. So now I'll remind you once again, please copy all the files you want to use for later to your local machine. And otherwise, we're open for a few questions now. So if you still have questions on this part, please, or on GW in general, we also have, I forgot to mention, 3 experts here. So we have Moritz Leutge as well as Antonio De Lesma from Dorothea Goltz's group. So they're, of course, specifically focused on GW, low scaling GW, also the GW implementation on GPUs. And we have Minye Zhang here from the Fritz Haber Institute, who is also one of the main code contributors for the periodic GW part. So if you have questions to all of them, please just feel free to ask them now. And yeah. Yeah, I think as a side note, we will probably close the cluster in 5 to 10 minutes, I think, right, Andre? And that should be hopefully enough time for you to copy your results if you're interested. But are there any questions or comments or general discussions you want to have? Yeah, Andreas said. So we will close it in 5 minutes. So that's the 10:35 CEST time. Any questions or comments? You can, of course, also give feedback. Hyungjun Kim asks, can SOC be coupled to GW? I think we have SOC. Do we have it for the periodic ones too? I don't know. Minye, I think we also have it for the periodic ones, right? I think Minye is typing something. Yeah. Yeah, I understand. For the molecules. Okay.
I think for molecules is available
Yeah.
to couple GW and SOC.
Yes. Yeah, I think so, right? For the molecules, for sure.
Yeah.
For the periodic ones, I'm not sure, but I think Minye wanted to answer something.
I think for now, no. For now, no.
Yes, yeah. Minye says it's not supported at the moment for the periodic one, but for the molecules, you can, yes.
Yes.